Have you ever wondered about the nature of the universe? How does everything work together so perfectly, from the tiniest atoms to the largest galaxies? Scientists have been asking these questions for centuries, and one theory that has captured the imagination of physicists and the public alike is string theory. So, what is string theory exactly? Well, imagine that the fundamental building blocks of the universe are not point-like particles, but rather tiny, one-dimensional strings that vibrate at different frequencies. Every fundamental particle that we know, such as electrons, quarks, photons, gluons, etc., are made up of these strings. The reason why a quark appears to be different than an electron is because both vibrate at different frequencies. These strings are very tiny. The length of a string is believed to be of the order of Planck length, i.e. 10 to 35 meter, or about 10 to 20 times the diameter of a proton. But why strings? The answer lies in the fact that string theory attempts to reconcile two seemingly incompatible theories: quantum mechanics and general relativity. In quantum mechanics, particles are described as waves, while in general relativity, gravity is described as a curvature of spacetime. String theory proposes that particles are actually tiny strings that vibrate, and that this vibration is what creates the curvature of spacetime that we perceive as gravity. As string theory progressed over the years, it was found that the theory required additional objects to work, known as branes. A brane, in string theory, is an object that generalizes the notion of a point particle to any number of dimensions. For example, a point is a brane of dimension 0, a string is a brane of dimension 1, a plane is a brane of dimension 2, and so on. Thus, a 0 brane is a point particle, 1 brane is a string, and 2 brane is a plane. Strings can attach to these branes at one ends or both the ends. Now, this may all sound very abstract and difficult to grasp, but stick with me, because there's more. String theory also proposes the existence of extra dimensions beyond the three spatial dimensions that we're familiar with. These extra dimensions are curled up or compactified in such a way that we don't perceive them in our everyday lives. But why do we need these extra dimensions? Well, the math of string theory requires them in order to work. In fact, string theory predicts that there are 6 or 7 extra dimensions, depending on the specific version of the theory. For example, spacetime is 26-dimensional in bosonic string theory, which is the older version of string theory, whereas in superstring theory, which is the new version of string theory, it is just 10-dimensional. This may sound like science fiction, but the idea of extra dimensions is actually a natural extension of our understanding of the universe. After all, there was a time when people thought the Earth was flat and that the Sun orbited around it. As our understanding of the universe has grown, we've come to realize that our perceptions are limited by our human scale and experience. But how do we test string theory? That's where things get tricky. One of the biggest challenges facing physicists is finding a way to test the theory experimentally. String theory predicts the existence of particles that are much heavier than anything we've observed so far, which makes them very difficult to detect with our current technology. As string theory has developed, physicists have proposed various different versions of the theory, which differ in their assumptions about the nature of the universe. Some versions of string theory suggest the existence of multiple universes, or a multiverse, where each universe may have its own set of physical laws and constants. This idea is still highly controversial, and there is currently no experimental evidence to support it. However, it is an intriguing possibility that continues to be explored. Whether or not string theory ultimately proves to be correct, its development has already had a profound impact on our understanding of the universe. It has spurred new lines of inquiry, prompted innovative research in mathematics and physics, and challenged us to think more deeply about the fundamental nature of reality. And who knows, maybe one day we'll be able to confirm the existence of those extra dimensions and parallel universes after all. But for now, we can only continue to explore the tantalizing possibilities of this intriguing theory.